Hello and welcome to Chapter 11, Section 2. Today we talk about the chi-square test for homogeneity and for independence. So there's actually two that we're talking about today, but chi-square specifically for this section is when we're dealing with two-way tables. So that's how you're going to know the difference between our last section where we did the goodness of fit test and this one where we're dealing with two-way tables. So in this section, because we have two different tests that we're talking about, obviously there's going to be differences between them. So I'm going to first talk about the chi-square test for homogeneity. Homogeneity is specifically for when your two-way table or your study deals with multiple samples at a time, which means the chi-square test for independence is only dealing with one sample. So when I say multiple samples or one sample, this means I'm talking about within the study itself, how many groups of people are they using? So like for this first example here, for the chi-square test of homogeneity, where there's supposed to be multiple samples, we're doing a study on does background music influence what customers buy. Market researchers suspect that the background music may affect the mood and buying behavior of customers. Let's see if this is true. So one study in a European restaurant compared 3 randomly assigned treatments where they had no music, French accordion music, and Italian string music playing. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. So here in this study, you notice that there's 3 randomly assigned treatments. So that means people are going into this restaurant and they're either going to get no music playing, French accordion music playing, or Italian string music playing. So each of those people that end up in whatever treatment, that's a whole separate group. So it's like having 3 different samples right here. So in this two-way table, we have our data that's being described. This is the groups of people where they listen to either no music, French music, or Italian music. And then this was out of each group, the entree that they ordered. So like 30 people who were listening to no music ordered French food. The 11 people who were listening to no music ordered Italian food, and so on. So the other type was the chi-square test for independence, where we're only dealing with one sample. And so in this example, we've got, we're talking about angry people and heart disease. A study followed a random sample of 8,474 people with normal blood pressure for about 4 years. All the individuals are free of heart disease at the beginning of the study. Each person took the Spielberger's trait anger scale test. Oh my gosh, that's hard to say, which measures how prone a person is to sudden anger. Researchers also recorded whether each individual developed coronary heart disease. So clearly, this study is just a random sample of people because they were looking at this random sample, and then within the sample, they looked at 2 variables, whether they had anger issues and whether they had heart disease. So when they're just looking at one sample, it's going to be a chi-square test for independence, and multiple samples in the study will be the chi-square test for homogeneity. So let's get started with the whole phantom process. As we write our hypotheses for these types of chi-square tests, the hypotheses now, because we're not just dealing with like a single mean or a single proportion, or even 2 proportions or 2 means, our hypotheses will now need to be written in sentence form because there's a whole lot to talk about here. So because we're writing it in sentence form, we just want to make sure that our context gets included. This is usually where we put in our parameters. So instead of the parameters and hypotheses being separate things, now we can kind of put all of it under hypotheses because our hypotheses will also include the context of the problem. So for the chi-square test of homogeneity, we're trying to test whether each of these distributions of the different types of food that people ordered would be different based on the different types of music that they're listening to. So really what we have is like a goodness of fit test, but rather than them giving us the proportions that it should be equal to, we're kind of comparing the different distributions instead. So it's like we're running multiple goodness of fit tests at the same time. So our hypotheses, our null hypothesis, is usually where there's like no difference, meaning nothing's different about it, the differences are equal to 0, is kind of how we wrote it in the past. So for a chi-squared test of homogeneity, we would say in a sentence form, there is no difference in the true distributions of entrees ordered based on music playing. So here, this is where I have the context of the problem because we want to make sure that the reader knows like what the study is actually talking about. But the keywords that we need to make sure we have in our null hypothesis is that there's no difference. because the alternative hypothesis then is the opposite. There is a difference in the true distributions of entrees ordered based on the music playing. I just write ... because it would repeat. Alright, so the next step in our phantom process is to name the test. So this is the chi-square test for homogeneity. I also want to state alpha equals 0.05 here so we know what alpha we are using. Then my assumptions and conditions is the same as what we've been usually doing. The random samples that we need, independent samples that we need, and then for chi-square it's the large counts has to be greater than 5. So in this problem we were told that we had randomly assigned treatments. So remember, randomly assigned treatments means that takes care of both the random and independent samples. Alright, so I'm just going to state that I have randomly assigned treatments. Finally, I have to check for large counts. It's when our expected values need to be greater than 5. To calculate our expected counts, in last section with our goodness of fit test, all we did was take n times the proportion, so our sample size times the proportion. Because we now have a two-way table, it's a slightly different formula, and actually is very different. So we're taking our row total times the column total divided by the total to calculate our expected count. And so this formula would calculate each expected count for each number within our two-way table. So it does not, like the totals of each two-way table, the marginal distributions, is not included when we calculate expected counts. So, because really we're focused on like the conditional distributions as to what our data actually is. So to calculate our expected counts of each of our data values here, I'm going to start with the people who listened to no music and ordered French food. So we observed a value of 30, but our expected value, our expected count, would be the row total of 30. So 30 is here, its row total is 99, multiplied by our column total. So that column for the value of 30 is 84. And then we're going to divide by our total, which is like the total of the entire table, which is 243. Okay, so when I multiply that out and divide, I end up with 34.2 repeating. Okay, then I'm going to do the same thing, but this time for the French and French. So the people who listened to French music and ordered French food. So that value was 39. My observed value was 39. The row total for that is 99. The column total was 75 divided by the total of 243. And that'll get me 30.5 repeating. And then I can do this and go through the rest of the expected counts for each of my other data values. Like if I do one more for, let's say, Italian and other. So for Italian and other, that would be in this box here. The row total would be 113. The column total would be 84 divided by 243. And that gets me 39.06. Okay, so obviously I can go through and do the rest of these expected counts. So I've done out the rest of my expected counts. The key thing that we're looking for is that all expected counts are greater than 5. That's how we meet our large counts condition here. Once we have all our conditions checked, then we can move on to our test statistic. So for our test statistic, it is the chi-square test statistic. It's the same formula as our last section, so you have the observed values minus the expected squared divided by the expected, and then out of each of those components we would add them together, and that would be our total chi-square test statistic. So obviously there is a faster way to do this, because if we were to go through each of our expected counts and take our observed value from our original data, subtract our expected count, square it, and divide it by our expected count again, that would take forever because we have 9 different values to do for that. So let's do this in the calculator. Alright, so we want to find the test for chi-square test. So it's not the GOF because that was our goodness of fit test. This is just a regular chi-square test. when you click on it, you end up with this menu where it just asks you for observed, expected, and then you calculate or draw. So the place where you would actually need to put your data, the square bracket A actually stands for a matrix. So a matrix is basically, if you want to think about it like a table or something like that in our case, that's really all it is, but mathematically matrices is the plural form of matrix. Matrices are used to calculate a whole bunch of stuff. So to get there, we want to input all our data not into a list, but in a matrix. On your calculator, if you look up right underneath the math button, you'll see in blue it says matrix, and it's the x to the -1 power button. So we're going to go there. So let me quit out of this first. So second mode, and then go into second matrix. So here you'll see the names of your matrices. We actually want to edit them though. So we're going to scroll over to edit, and I'm going to edit A. So hit enter. So it'll give you this option, blank by blank. In a matrix, it's basically saying like how big do you want your table to be, and it's all, the first number is always the number of rows. The second number that it's being multiplied by is the number of columns, and it's not really being multiplied. It's like a 5 by 4 whatever. It's just the dimensions of the matrix. So for us, because we have 3 rows and 3 columns for our data, it'll be 3 by 3. Okay, and once you have that typed in, it'll give you like a little table where we can type in all of our data. So this first box is going to stand for my people who listened to no music and had French food, so that would be 30. When I hit enter, it goes left to right, and then it goes to the next row after that. So we're just going to continue typing in our numbers. Okay, so I've got my matrix all filled in. So now that this is filled in, I'm going to go back to my test. So second quit, back to my tests here, to chi-square test. Okay, so now I've put my observed values into matrix A. It wants my expected values to go into matrix B, but we don't actually have to type in our expected values. So that's the nice part. This whole part where I showed you how to calculate expected counts, that is something that you need to know the formula for, but you don't actually have to do it yourself because your calculator will do it for you. So the expected counts, I'm just going to leave that matrix blank. And you don't even have to touch matrix B at all. You really just need to put in your data into matrix A, and then you're done. Go to calculate. So first, when it gives you our statistics here, the chi-square, that's our test statistic. So our test statistic is 18.279. P equals, that's our p-value. So we have a very small p-value here. And then it also tells you what the degrees of freedom is. So let's talk about a few of these things. So we got our test statistic is 18.279. I'm also going to write down my degrees of freedom because we want that to be part of our process, either in the odds section or the test statistics section of our Phantom. The formula to actually calculate the degrees of freedom is also different than before. Take your rows minus 1, multiply it by columns minus 1. So our data set here had 3 rows and 3 columns, so 2 times 2 is 4. So that's how we're calculating our degrees of freedom. Our next step was odds, and our p-value, the probability that chi-square was greater than 18.279 was 0.001. Some small p-value there. So this means that since our alpha level was 0.05, we would reject HO because we have a small p-value compared to our alpha level. And as usual, our conclusion is going to be the same as before, so nothing crazy there. I do want to show you though in the calculator. So earlier we were talking about the matrix B for where our expected counts go. We didn't have to put anything into it because our calculator was going to calculate all those expected counts for us, which also means that if you are to do this problem on your own, like fully using the calculator and not just me teaching you how to find expected counts and stuff like that, you can just go ahead and do the whole thing in your calculator first and then kind of go back and fill in what your expected counts are when you check your conditions. Because now when I go into matrix B, I'm going to go back to matrix, and again, you'll see now that in matrix A, you have something there. It's a 3 by 3 matrix. You also have something in matrix B now. It's just 3 by 3 matrix. You want to actually edit them though to see the actual values in each matrix. So if I go back into matrix A under edit, it'll just take me back to the numbers that I entered. But now if I go into matrix B, these are all my expected counts. So these are the ones that we calculated ourselves. All those numbers are the same. So you do not need to calculate your own expected values. You just go into the calculator, have it do the chi-square test, and then it'll calculate everything for you. Fill it in, make sure everything's greater than 5, and then your large counts condition is checked. All right, and finally, we can make our decision. So this is the same as before. Our p-value of 0.001 is less than our alpha level of 0.05. We reject HO. There is convincing evidence that there is a difference between the true distribution of entrees ordered based on the music playing. So we did actually find out based on this data that whatever music is playing does affect your distribution of entrees ordered. Just like our chi-square goodness of fit test though, anytime we reject HO, we also need to see which of these proportions was actually different. Which of the distribution out of each of our data values is the most different, what contributed the most to that chi-square test statistic. In order to find that, it doesn't come just as easily into our calculator as we normally have it, because when we did the goodness of fit test, it kind of calculated all your components easily. The chi-square test, though, in the calculator does not do that, only for the goodness of fit. So to find the component with the highest component of our chi-square test statistic, then what we're going to need to do is to go into our lists and actually enter in all our data values that were originally in the matrix. So we'd have to type in all our values here. I started with the first column, 30, 11, 43, and then keep typing in the rest, 39, 1, 35, and so on. And then in list 2, we're going to type in all of our expected counts. So you should have them written down because you did your check for the large counts already. So when you type it in, so I was typing like top to bottom of each column, you're going to have to make sure you go the same direction with your expected counts. So each expected count has to match the observed value, or like match the spot, the position of your observed value. I know it's really exciting watching me click numbers. Okay, done. Okay, so we have all our observed values, all our expected values, and now we can go into L3 and do our chi-square formula for our test statistic. So remember that was observed minus our expected squared divided by expected. When I do that, I'll get each of my individual components. I'm looking for the biggest one. Be careful as you go through though, because sometimes, like for this one, it looks like it says 2.9, but really there's an E in it, so that means it's scientific notation. So this is actually a really small decimal and not a number 2.9. But it looks like our biggest component is going to be right here. I've got a component of 7.7042. It's bigger than the rest of my components, even if I scroll all the way down. My second largest one would be this 6.4 over here. But 7.7042 is my biggest one. And if I look at my original data point, this was the one that was observed. So that means this was my French music, Italian entree ordered. There was only one. But we had originally expected there to be 9.6. So for that value, we only observed one, but we expected 9.6, so we got a lot less than expected. So I would word this as, in particular, the number of Italian entrees ordered while French music was playing was much less than expected. All right, so anytime that you reject HO, that's something you have to find, the largest component. All right, so that's the full phantom of a chi-square test for homogeneity. The other one I want to talk about is the one for when we're only dealing with one sample but still have a two-way table, which is the chi-square test for independence. All right, so in a chi-square test for independence, we're basically trying to see, since we are only dealing with one sample, if these two characteristics of this one sample are related to each other. Is there independence between these two variables? Because in this problem, we're looking at their anger level and whether they have heart disease or not. So we want to see if these are related. Is there some sort of association with them? Are these two variables independent? That's why it's called the chi-square test for independence. So for our hypotheses and our parameters, since we are dealing with sentences for our hypotheses, then our null hypothesis should be that there's no difference between them, or if you want to think about it as there's no association between these two variables. In other words, they are independent of each other. So for my null hypothesis, I can write it as there is no association between anger and heart disease, or you can also word it as anger and heart disease are independent of each other. So both of these would work. Our alternative hypothesis would just be the opposite. So there is an association, or anger and heart disease are not independent of each other. Done. All right, so our next step is to name the test, which is our chi-square test for independence, alpha equals 0.05. Assumptions and conditions, this is the same as what we normally do. So we have a random sample in this problem. It was given to us. Independence here, because this study was not an experiment, they didn't impose any sort of randomized or randomly assigned treatments, then we can't use random assignment as our random and independence check. But our population that we're dealing with here is people with normal blood pressure. So our sample size was 8,474, so this has to be less than 10% of the total amount of people with normal blood pressure. Also, just, wanted to really quickly point out, this is an actual observational study. It's not even an experiment because we're not imposing any sort of treatments on these people. We're just trying to measure how angry are they and do they have heart disease. So we're not actually forcing any treatments. We're just observing their anger level and heart disease or not. Okay, so next, let's do our large counts. So this is the part where we're not going to calculate our own expected counts because we don't have time for that. We're just going to use our calculator for everything here. So in matrix A, I'm going to type in my data here, not including my total column and rows. So going into, got to turn on my calculator first. So second matrix, we're going to go into edit, and we want to edit matrix A. So here we have 2 rows and 3 columns, so this is a 2 by 3 matrix. Remember, it starts with rows. So 2 times 3, and then I'm going to start typing in my numbers. I have 53, 110, 27, 3057, 46. So sorry that you have to listen to me click through all these numbers. It's really hard to do on the computer versus an actual calculator. All right, I have my matrix now. Okay, so now we can go into stat test, chi-square test. So our observed values are in matrix A, matrix B. I know it still has the stuff from before, the last problem that we did, but it doesn't even matter. It will change it for me. So I'm going to go down and calculate, enter. Yay, there's my test statistic, there's my p-value, my degrees of freedom is 2. Great, but really right now all I'm interested in are what are my expected counts. So I'm going to go back into matrix, go over to edit, and I want to look at matrix B. So notice how it says 2 by 3 now because it changed it for me. There we go. So as you can see, all our expected counts are greater than 5, but we do need to show our reader that they are greater than 5, so we do have to write this out. In general, my expected counts, I don't worry too much about how many decimals and whatever. I just do 1 decimal place so that the reader knows, like, these were decimal numbers. And I'm just going to write all these out. All right, so real quickly, I wrote down all my expected counts. They're all greater than 5. Check. Test statistics. So again, this was straight from the calculator. We got 16.08. The degrees of freedom would be the rows minus 1 times columns minus 1. So there were 2 rows, 3 columns. We multiplied to 2, and that's what the calculator gives us as well. Our odds. So our probability was 3.2 something e to the negative 4. So this means this is a scientific notation probability. So that means we are moving the decimal place to the left 4 times. So it ends up being 0.0003, which is a super small probability. So I'm not going to write out the conclusion for you here this time because it's exactly the same as before. We compare our p-value to our alpha level. It is less than, so we reject HO. We do have convincing evidence that HA is true. There is an association between the anger level and your heart disease. And because we are rejecting HO here, you would need to find your largest component again using the lists. All right, I don't want to make this video too long. Thank you so much for watching. See you next time for the last video of this class ever. Oh my goodness, I can't wait. Thanks for watching. Don't forget to like and subscribe. Bye.